So this video is going to cover the notes for section 1-2. We're dealing with quantitative variables and quantitative data and the types of things we can do with that. We can make comparisons, we can describe the distribution with quantitative data, and we're also going to talk about a number of different graphs and how to make those graphs when the data is quantitative. All right, before we get into the notes, I just want to remind everyone that they must have a graphing calculator for this class. It's not an option; you must have one. If you're an older sibling has one, you can borrow it from them. If you have an 83, we can make it work. It's kind of an older calculator. Fewer and fewer students show up every year with an 83. It'll work for most things. It's not user-friendly. You're going to have to remember how to do certain keystrokes on your own. Just not as user-friendly, but it can work. I would say if you have an 83 from a previous class or from a sibling, we can make it work. Don't buy a new one. 84, if you're going to buy one, 84 plus is what I would recommend. You can sometimes buy them used on Amazon for 60, 70 bucks. A new one's probably 100, close to 100, 120 bucks. You can buy this third one, which is like colored, and it's chargeable, it's rechargeable. The other two, 83 and the 84, have just 4 AAA batteries in them, and sometimes it's nice because if the battery dies, you can just put in new calculators. You don't have to worry about charging it. These are pretty expensive. I think they're probably $150, $160, a little bit expensive. I do have some 84s that I've designated as loaners that I will sign out. Like you sign out a textbook, you can sign this out for the entire year if you are in financial need and you don't think that you can swing buying a calculator. You have to have one for the class. So if you don't have one, you're going to have to drop the class, basically. So if you are unable to financially swing it, come see me during lunch and I'll sign one out. I have a handful of them that I designate as loaners for the year. If you have some other form of graphing calculator, a Casio or whatnot, I demonstrate a lot in class how to use a TI, either an 83 or an 84. If you have another type of calculator, you can use it, but I'm going to be of no use to you as how to use it. If you can Google and figure out how to do what we need to do, that's fine. There's no requirement for the AP test that you use a Texas Instrument, but that's what I'm familiar with and what I've been using for 25 years. So it's the only one that I can sort of help you with. So, if you have another one, come talk to me. I'm sure you can make it work. But if you have any questions on what kind of calculator to get, come see me at lunch. All right, so what are we going to do in this section with these notes in this video? We're going to look at the different types of graphs, dot plots, stem plots, start to talk about how we describe a distribution of quantitative variables. We'll talk about the shape, different things that we're going to look at about the shape. We're going to make and interpret histograms. And then what do we do when we want to talk about comparing two different distributions? All right, so a dot plot. So this is one of the simplest ones to make. You probably saw that I did an example of this during one of our first classes. When we talked about swimming with dolphin example, I just created a real quick and simple dot plot on the board in class. So it's easy to do by hand, and we're going to have you do one right now. So how do you make it? First, you got to create the X or horizontal axis, essentially a number line. And as you would a number line, make sure the spacing is consistent. And it's the variable that we're, of interest, the quantitative variable of interest. Make sure that you put the scale, make sure that the minimum and maximum points in our data can actually fit on that scale. And then we're going to make dots above, vertical dots and a vertical sort of line above each of the values on our axis. Again, this will make more sense when we get to an example, which we're going to do right now. All right, so here are, let's see, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 25 data values here. It's the number of goals scored per game by the 2012 U.S. Women's soccer team. Okay, so you can see that at one time they scored one game they scored 2, another game they scored 1, another game they scored 5, and so on. So this is the data from 25 different games in 2012. Okay, so the first thing we want to do is we want to make a scale. So you want to look at what's the minimum. Okay, the minimum is 0. The maximum, looking through the data value, the maximum appears to be 14. So clearly you don't have to start with 0 and 14, but you just have to use a scale that will fit those on. We don't want to start at 0 and go up to 100. We want to use a scale that's appropriate. Could we go from 0 to 15? Yeah, that would be fine. But generally you want to make sure that the scale doesn't bunch all the data up. So, starting with the minimum and ending with the maximum is not generally a bad idea. All right, so now what we do is we simply go through each data value and we put a dot on the graph to represent it. So the first number is a 2, so I put a dot there and I cross that out. All right, and the key is dots should be the same, all the dots should be the same size, and the spacing for them should all be consistent as well. So next data value is a 1, so I put a dot at the 1 spot, and I cross it out. You don't have to cross them out, but you should at least, keep your finger next to it to make sure that you are not using it twice and that you've used all the values. All right, so the next one's a 5, so I put a dot at the 5. The next one's a 2. So I put another dot right above the dot that's already there. So I'm creating sort of this column of dots. Every time I get a 2, I'm going to put the same size dot and the same spacing. All right, so a 0 is the next one. And I just go through these one at a time. 1, I put another dot above the 1 and cross it out. 4. And cross it out, and so on. So just got to be careful too that when you cross them out, you're not obliterating them. You want to make sure that if you want to go back and check your data, that your numbers are still there. All right. So maybe you just hold your finger over the number you're using, and just keep concentration. So you just keep this up, keep going until you've got all of the data plotted, and you use every single one. Again, each dot should be the same size. Each of the spacing of the dots should all be the same. So you're creating sort of this graph, and if I made, for example, if I made the spacing between the dots above the 2 bigger, then it would kind of give more weight and make look like there's more 2s. Yes, it would look like there are more 2s. For example, looking at this very clearly, there's more 4s than anything else. But that ability to interpret this graph depends on your dots being all the same size and the spacing all being consistent. And we'll talk about what shape this dot plot is in the next couple of slides. All right, so we kind of want to look at, say, all right, so we've plotted this data, what are we going to look at? So we want to look at patterns, overall pattern, see if there's a pattern in the data from the graph, and then any departures as well. So what we really want to concentrate on is shape, center, and spread. what's the shape of the distribution? Where is the center? We're going to talk about center more in future section, but center is either the median or the mean of the data. Spread is generally range or standard deviation. Again, we'll talk about those more details later. And then the last thing you want to look at is, are there any outliers? So looking back at your data for the women's soccer team, I would say your data 13 and 14 were probably outliers. At this point, we're just going to say any data that's different than all the others. So 13 and 14 are clearly bigger than the others. We will have more of a formulaic approach to determine whether data value is an outlier or not in the future. But for now, we're just seeing, does it fall outside the pattern of the other data? And so 13 and 14 definitely are data values that are extremely higher than the rest of the data. All right, and we use this acronym SOX, shape, outliers, center, and spread in no particular order, but SOX is a good acronym for remembering the 4 things you must discuss whenever you're asked to describe the distribution for a quantitative variable. All right, so let's talk about shape. There's more than just these 3, but these are ones that we use a lot for describing shape. So symmetric, the data has a symmetric distribution if the left-hand side and the right-hand side look generally the same. They're not going to be identical. They're not going to be mirrored images of each other. Real data tends to not be so nice sometimes. But if they're not symmetric, then we'll generally say it's roughly symmetrical, and that word roughly will sort of hide a multitude of sins. Okay, skewed right or positively skewed means that the tail, or sort of like the right side of the data of the graph is longer than the left. If it's left skewed or negatively skewed, because if you think of a number line, the number line goes to the left and it's negative when it goes to the left in the negative direction. So it's skewed to the left or it's negatively skewed if the graph is much longer or the tail goes out to the left. All right, so let's look at the examples on the bottom of your page and take a second and write on top of each one whether it's skewed left, skewed right, or symmetric. Okay, so the first one, now again, it's not perfectly symmetrical, it's not a mirrored image, but it's fairly symmetric. All right, the next one, the one in the middle, the tail goes to the left. So this is skewed left or negatively skewed. There are going to be times when the left and right skew, using that as a description is going to be a little confusing. So you might get used to saying negatively skewed. In this case, either one would work, but this one is left or negatively skewed. Okay, and then the last one, the tail goes over to the right more, and so the tail tells us the skew, and so this is right skewed or positively skewed. All right, so when we look at comparing distributions, so this is these are dot plots for the size of households in South Africa and for distribution of houses, house sizes in the UK. And so we will want to, when we compare these, we want to use our shape, center, spread, and outliers. Okay, we'll talk more details later, but clearly the households in South Africa have a bigger range of data, so the spread is larger. So we'll go into more details in the future about how to make these exact comparisons. We'll talk about the shape. Clearly, the South Africa is skewed right, whereas the UK data seems to be a little bit more symmetrical. The centers, we'll talk about centers. Median is usually what we'll use. And so we'll say, oh, the median for South Africa of about 6 seems to be larger than the median for UK, which is about 4. Okay. And then the spread, we'll talk about the range. We'll take the max minus the min, that will be the range, and then we'll compare those. And then we'll talk about outliers as well. We'll say South Africa seems to have an outlier at 26, whereas the UK data doesn't seem to have any outliers. So we'll talk about the shape, center, and spread for both of these distributions kind of at the same time. All right, the next type of graph we're going to talk about is stem plots. You might have looked at these in middle school. Seems like years ago people would have been exposed to stem plots, or what we call stem leaf plots, in middle school. But nowadays it doesn't seem like they do that in middle school. They push you into Algebra 1 quicker, and so you don't get this exposure. But we call them stem plots, but some places might refer to them as stem and leaf plots. All right, so first thing we want to do is we want to separate the data into its stem and its leaf. And so generally the last data value, often the units place, will be considered the leaf. It's the final digit, and everything else is considered the stem. All right, we put the stems in a vertical column, smallest to largest, top to bottom, so small to large. And then we write the leaves next to them. The leaves should be in order next to its stem. Sometimes we'll make it and then rewrite it, or just be careful and write them in order the first time, and then 3 and 4 are sort of the same step. And then we also want to make a key. Now, none of this, I'm sure, makes any sense. It'll make more sense when we get to an example, and let's do that now. All right, so we asked 20 female AP statistics students, how many pairs of shoes do you have? So 20 different responses. You can see the first female student said that they had 50. The next one said 26. The next one's 26, and so on. So we have 20 different data values. So the first thing we want to look at is what are the stems. So in the first data value, 5 is the stem, and a 2, and a 2, and a 3. Those are all the stems. So the tens place is the stem, the units place is the leaf. All right, so we make the stems. We start with 1 because that is the lowest. That data value is 13, right? So we have to have a 1. The largest data value appears to be, what, 51? And so we need a 5 for the 50s. We don't have a 6 because we have no 60s. We have no 0 because we have no single digits. Okay. If, for example, let's just say we had no one that had a 20, 20, 21, 22, 23, no one in the 20s, we would still need to leave the 2 there because you got to think of this as like a scale. And so we can't jump from 1 to 3, even if we didn't have any 20s, which we do, we have 20s, but if we didn't, we would still need that 2. So missing data values doesn't matter. The stems still have to be continuous as we go. All right, so now we want to look at putting down the leaves. So one at a time, we take each of the leaves and we put them as we come across them. However, these are not in order, and we need them in order, so we would rewrite them in order, or just be a little bit more careful. Look at the teens, so a 3 and a 3 and then another 3, sort of cross them out as you come across them, and then you don't have to sort of rewrite them. All right. And so this is the final goal here, is to have them in order. And then we want a key. So we would write a key. And so it looks something like this. Key, and then we would have 4 and a vertical line and a 9, and say, okay, that represents a student who has 49 pairs of shoes. Make sure you're using, in your key, make sure that you're using a value that's in our graph, in our stem plot. So in other words, I wouldn't say 9 vertical line and a 2, because I don't have a 4 and a vertical line and a 2. I won't, because I don't have any 42. I don't have 42 as a data value. So use one of your data values in your key. That kind of makes sense. All right, so we have other ways of creating stem plots, and sometimes we will split the stems. So in this case, we probably don't really need them. For this data set, we don't really need to split the stem. But if we had a lot of data bunched up on 1 or 2 stems, sometimes we'll split the stem. So here we're including males now. We've asked 20 males, how many pairs of shoes do they have? And so we're going to create what we call a back-to-back stem plot. So there's going to be leaves coming off of these stems in both directions. So, in the right side, I think I'm going to put the males, and on the left side, I'm going to put the females. And so this is a good way to compare the distribution for males and females because it's on the same scale. All right. So at the same time, I'm splitting the stems. So notice we're dealing with males, and there are some single digits. And so I have zeros, and so 0, this first 0 represents any data value, any leaf off to the side that would represent people who have 0 shoes, 1 pair of shoes, 2, 3, or 4. The second 0 here, this will be stems off to the right, which would be data values that are 5, 6, 7, 8, and 9. And then 10 would start with 1, 0. So the 10s would be on the 1 here. So that'd be 10s, 11s, 12s, 13s, and 14s. The next one represents 15, 16, 17, 18, or 19. So each of these split stems still has the potential for having 5 different types of leaves off to the right or left. All right. So if we look at putting the males to the right, we would look like this. So we have one student who has a 4. They're on the first 0. 5, 6, 7, 8s, and 9s show up on the second 0. 10 through 14. The next one, even though there aren't any there, we still have it. Remember, we can't just get rid of a stem just because there are no leaves off of it. We have to have a nice consistent scale. Now you might say, why do we have 4 and 5 showing up? None of the boys have 4s and 5s, but remember the females do. And so we have to make sure that our stems in this case accommodate both the males and the females. So we put the females off to the left, and we have them actually in reverse order now. The smaller ones, smaller leaves, are close to the stems, and they get bigger as they go out. So the females look like almost they're in reverse order. For example, if we look at the 20s, it's 22, 23, 23, 24. They get bigger as they go out. The males get bigger as they go out away from the stems. Okay, so this is a good way to do a side, it's a back-to-back stem plot. It's a good way of comparing these two distributions because they're on the same scale. And also don't forget your key. Okay, and again, use a data value that's in one of the two. I generally, we have a 3 vertical line 5, so I'm going to use to represent a data value that's on the right side, or in this case, the males. So 35. I wouldn't use 25 because there are no males that have 25 pairs of shoes. All right, now let's talk about how to create a histogram. This is another very popular type of graph used for quantitative data. All right, so how do we make a histogram? First, we're going to divide the data into specific class widths. So we're going to take the data and break them up into classes. We're going to look at either the count, which is frequency, or the percent, which is relative frequency. We're going to label the scales on the axis. So the scale, the x-axis is going to be the variable we're interested in, and then the vertical axis, or the y-axis, this is going to be either frequency or relative frequency. In this case, the vertical bars should touch each other. All right, so the bar graphs, we always left a gap. That was categorical data. Here with quantitative data, for histogram, we always connect the bars. The bars are touching. Okay, so let's do an example. So here we have data that represents the percent of residents in each of the 50 states that were born outside of the United States, or foreign-born, residents. So if we look, the first class is from 0 up to, but not including 5. So there were 20 states that have a percentage of foreign-born residents between 0 up to, but not including 5. So 0 up to 4.999%. If a state has 5% of its residents, then it would be counted in this 13. So 5% up to 9.999%. There are 13 of those states that have percents of residents born outside the United States from 5 up to, but not including 10. And then the next class is 10 up to, but not including 15. So to less than 15 is the idea there. Okay, so we want to make a scale that accommodates our classes. So we want to make sure that we start with 0 and we go up to 30. And so notice we had from 0 up to 30. And then here I decided to go with counts rather than relative frequencies. So frequency rather than relative frequency. And I'm starting at 0 and going up to the max, which is 20. Okay. And then I simply make a vertical bar for each. So starting it from 0 up to 5, that will be my first bar, and so on. Okay, so the first bar goes up to 20. The next one from 5 to 10, up to but not including 10, is going up to 13, and so on. Clearly, we can look at this, and now that we have a graph, we can see that this is skewed to the right. The tail goes off to the right, skewed to the right, or positively skewed. Notice there are no gaps between these like we would see in a bar graph. So for bar graphs, we leave a gap between the bars so that just looking at it very quickly, we can see, oh, this is a bar graph. Now, let's say, for example, there were no states that had residents between 20 and 25. So what I'm saying is, let's assume this number were 0, then this bar wouldn't be here, and that's fine. There would be technically a gap between that, but that's because there's a gap between the data, not because we're putting gaps between the bars. Okay. All right, so some things to be careful about, some common mistakes that people do with histograms. First of all, don't confuse histograms with bar graphs. Histograms are used for quantitative, numerical data. Bar graphs are used for categorical data. Classes should be of the same width. There are ways to get around that, but for us, we're keeping it simple. Class width should be the same, period. If we're doing a comparison between two different distributions, generally the number of data values are going to be different, and so we should use percentages or relative percentages there. We're going to look at an example of that where that can be confusing in a minute. All right, and then just, sometimes people put data in an Excel and just create a graph, but doesn't necessarily mean anything because they didn't choose the right type of graph. So just because it looks nice doesn't mean that it's going to be useful. Okay, so here's an example. This is actually categorical data, but it visually demonstrates the importance of using relative frequencies when you're comparing two different distributions. So here we have, we've asked girls, sixth graders, girls and boys, what's most important for school? Is it getting good grades? Is it being popular? Or is it participating in sports? And you notice that there are fewer boys and more girls in this survey. So if we create a graph, like we did here, but use frequency, then there's kind of a weird thing happening here. Girls it seems like girls think that grades are more important, popularity is more important, and sports are more important. This seems weird. How can they feel like all three of these things are more important? And it really isn't. The problem is there are just more girls in the survey. So of course, if we use frequency, those bars are going to be higher. Okay, and again, this is a bar graph, really more talking about the data we saw in section 1.1, but this is talking about the importance of using relative frequency when we are comparing two different data sets, particularly when the data sets have different number of observations based on, for example, gender. All right, so instead of using frequency or counts, like we did in the previous one, we want to use a relative frequency or percentages. Now notice my percentages here are as decimals. Your percentages or relative frequencies can be written as a decimal or a percent. Doesn't matter, I'm using decimals here. 0.49, or I could come over here and put that as 49%. Doesn't really matter. Okay, generally that's not going to matter one way or the other in most graphs. But here I just did them as decimals. Okay, notice now something interesting happens. Here, if you look at sports, it looks like sports are more important to girls than to boys, but in reality, it's the reverse. And that has to do with the fact that they weren't the same number of observations for girls and boys in our survey. It's 21% versus 23%. So boys tend to think sports are more important in this group. Girls tend to think that popularity is a little bit more important. They're relatively the same for grades, 49 and 48%. Okay, so it's really important that you use relative frequency whenever you are comparing two different distributions, particularly when the number of observations in the two groups are different. All right, so your homework for section 1.2 is listed here. Remember that the homework exercises for each section do not start counting with 1 again. So if you look back, the homework for section 1.1 was problems 1 through 36. 37 is actually the first homework assignment, first homework problem in section 1.2. So the homework problem numbering continues as we go through the chapter. So you're starting really with the first homework problem in section 1.2. It just happens to be number 37. And this homework would be due next class.